forms of energy there are. Okay? So take a moment, think to yourself, and we're gonna see, what do you call it? Partner pair share. So we're gonna do that. All right? So, so think, then pair, then share.
Or you can just do pair share.
Pair share.
Pair share, there's think pair share, there's a rethink pair share.
So many acronyms.
Well, the hint.
Thank you.
But pair share.
All right. So you've had a minute to think about it, talk it out. Somebody give me one. So group, you guys give me one.
I liked heat.
Heat. All right. So that's heat. And we've talked about this previously in class, and it's also known as internal energy. And what about one over there? I heard some ones I liked over there.
Potential.
Potential, yeah, potential energy. Potential, let me actually spell this correctly. And kinetic energy, right? And those are the ones that we're really going to focus on. What are some other interesting ones?
Well, you can do mechanical too, where it's potential plus kinetic, or no?
Yeah, well, that's where we're going to get to that. So, potentially kinetic, yeah, that's total mechanical energy. And we'll get that a little later on. What else do you have? I mean, so we have heat, right? What's coming out of the light bulbs right now? Light, yeah, light can be a form of energy.
We're all like, I don't know.
How about, what am I projecting right now? Sound, right? So sound's a wave. Any wave can have energy in it. So sound's another one we can put up here. And this is going to be hard to read for you guys across the room. I'll amend that for next time I do a lesson. And what about what's coursing through? What's going through the lights right now?
Electricity?
Electricity, right? Good. So I have a question for you. Do you think that energy can change between these forms?
Yes.
How so?
Well, okay, if you're on like a roller coaster and
Mhm.
you're going up and you get into the top, that's one from kinetic potential.
Yeah, very good. How about another one? What about one using the lights? Since I've been focusing on those for whatever reason.
I think lights and maybe a boombox do the same thing. It starts electricity, but turns into light.
Yeah, exactly. And boombox turns into sound, right?
And like.
Yeah. Yep. All right. Cool. So now let's do a quick review of potential and kinetic. And this guy, nope. So we have potential energy, which we talked about, is the energy that's associated with an object by virtue of its position. And that might sound kind of strange. You're not sure exactly what that means. But, because like how can changing a position change the amount of energy something has, right? But it has to do with, what we're going to talk about specifically is gravitational potential energy. And so the example Elizabeth gave earlier where as something gets higher up has potential energy, that's the higher off the ground it is, the more potential energy it has. And that's related through an equation that I have right up there. It's potential energy is equal to mgh. So P here is potential energy, M here is mass, G is something we've talked about previously in class, that's the acceleration due to gravity, and H is the height above the ground. Okay, and the kinetic energy, that's the energy that's possessed by an object due to its motion. So that equation right here that we would have gone over in the previous classes review is kinetic energy T is equal to 1/2 mv squared. All right, and now we get to the more interesting part of the class. we're gonna do a little experiment because we all learned last time that I like hands-on things. So I have a bunch of ping pong balls. And we are going to take a look at them, bounce them up and down, drop them from different heights, and take a look at how they react. So while you're doing this, I want you to think about what happens to the potential and the kinetic energy of the ping pong ball, okay? So, try to, hold it to a certain height, drop it, see how it reacts, hold it higher. If you want to, you can try actually putting energy into it, so if you give it a little push,
Whoa.
right?
It does look like it slows down on the paper. Like when it gets this little trajectory there, it kind of dies.
Yeah, yep.
Oh, no, it didn't answer. Oh, there we go. It's very soothing.
It's about
So
force.
Carter, I'll discuss, make some observations about what you're seeing as it goes. You know,
She was right. I saw the paper.
Oh, yeah.
Bouncy.
nice, nice.
Higher?
What is it? Does it bounce up to the same height?
Every time.
Like after you drop it?
Oh, there it goes.
Oh, where is it?
Like rolled down my leg off my foot.
My ping pong ball.
Well, think of this. Does it bounce up to the same height that you drop it?
No.
Why not? It's tired, yeah. It has less energy, right?
Oh, okay. I was gonna say gravity.
Where does the energy go?
Yeah, maybe
That is the
gravity is.
Pulling it down.
That it can't.
So it
go to
can't-
that-
yeah.
Reach that height?
Not in this case. So
No.
it's actually
Definitely
think
not a
about it when you
physics
drop it.
major.
What happens when it collides with the ground?
It,
Smashes.
Or the table?
Bounces.
ah.
The table does, yeah.
Good catch.
What do you hear?
So some of the energy lost in sound?
Yep, some of the energy's lost in sound. And then what else is it going through? It's going through something, right?
Air resistance.
What does it have to, yeah, it's air resistance. So it's losing energy as it goes by the air. Good. And now I want to take a closer look at what exactly we were just looking at.
Should probably take back the ping pong ball.
Yes.
All right, ready? Can we throw them at you?
That's probably not the best idea. No, hand them out. Not that I would mind, but given that it's a classroom setting.
Oh, you probably would if there were
You could have like a
25
huge
students.
shop.
I was gonna say you should hold the bag open and just let them throw.
Plus, these classrooms tend to have tile floors, so that wouldn't be good. So this is a scenario we're just looking at, a bit more pronounced. But we want to look at it during specific situations. Are these functional?
Mm.
Nope. So let's think about the potential and the kinetic energy, right? So we have potential energy is equal to mass times the acceleration due to gravity times the height. Okay? So right here, see there's a little potential energy right here, it's kind of getting in our way. You have this height, right? And then, so you're gonna have a certain amount of potential energy associated with that height, with the ball right there, okay? Does it have any kinetic energy?
The ball.
Yeah.
When she's holding it like that?
Mm-hmm. No, right? Because the velocity, the speed of the ball is zero. So if you look over our equation, that's going to zero out that whole equation. So this has only potential energy right now. Now it's dropped. So let's look at it at this point. Does it have potential energy? It does, right? Because it's a certain height above the ground. Does it have kinetic energy right now?
Yes.
Good, good. Yep, it does. What about if we looked at it like right here? So right before it hits the ground. So the height is essentially zero. Is it having potential energy?
No. It's not yet zero, so we can still have something.
A tiny bit. So let's say if the ball is, I don't know, 3 centimeters, then the space between it and the ground is something like, I don't know, 2 nanometers. essentially no potential energy. So the question that comes up is, let's pretend that there's no air in this environment, okay? So she's having a really bad day. As the ball drops, so here you have only potential energy, right?
She's wearing one of the
Here you
masks.
have a mix of potential and kinetic. And here, do you have any potential?
No.
No. Do you have any kinetic?
Yeah.
Yeah, because that's when the ball is actually going to go the fastest, right? Because it's from falling this distance. So the question that arises is, how does, so when, got lost in my thought. So we talked earlier about how potential and kinetic make up total mechanical energy, right? Do you think, in this sort of environment with no air resistance, so the ball's not, transferring energy to the air, that the ball would lose energy as it fell?
Total energy.
Would lose total mechanical energy overall.
No air resistance.
No air resistance. Hasn't hit the ground yet.
No.
No.
No, in this case, it would not lose any energy. So what happens is potential energy transfers completely into kinetic energy as the ball falls. And it turns out, if we had taken your ball drop experiment and made a graph of it, unfortunately, I kind of wanted to bring a prober in, but didn't know if I had the capability to do that here. Oh, no, I can't change slide. I guess we'll call it though, because I think
If you
time's
go